our last episode, we delved into the kinetic molecular theory. We saw how molecules behave in solids, liquids, and gases. Today, we will take a closer look at the solid and liquid phases of matter. We will also discuss the basic types of solids, surface tension, and humidity. Here are a few samples of solids. Can we classify them into basic types, just as we classified matter into mixtures and substances? Yes, we can. We can group them into two basic types. The first group are the crystalline solids. Just like these models of crystalline substances, sodium chloride, iodine, iron, and silicon dioxide. The basic building block of the lattice is a unit cell. The unit cells, stacked together in an orderly pattern, build up to form the crystal. We can group the other remaining samples of solids into a second type called amorphous solids. This time, the particles are arranged in a random manner. Because of this, they usually appear powdery, dull, or opaque. Most amorphous solids, like glass and plastics, are made up of long chains of atoms and big molecules that do not stack up well. These substances solidify before their molecules can form neatly arranged structures. Here are two solids made up of the same substance: quartz, a mineral, and glass, usually a man-made material. Both of them are made of silicon dioxide or silica, but quartz is crystalline while glass is amorphous. Given enough time, the particles of quartz form an orderly pattern under the earth. When silica melts and hardens, it forms a glass. The atoms of this glass make up a disordered network. How else do we distinguish between crystalline and amorphous solids? The melting point of a crystalline solid like picric acid can be determined using this setup. Picric acid melts sharply at 122 degrees Celsius. What about an amorphous solid like butter? It melts gradually over several degrees range of temperature. Why do these two types of solids melt differently? This has to do with the orderly arrangement of molecules in picric acid and the disordered arrangement of molecules in butter. To help us understand how crystals develop, Arceli da Silva will prepare a crystalline solid with very simple equipment. First, she will prepare a supersaturated solution of nickel sulfate. Start by heating the solvent to 70 degrees Celsius. She adds solute until no more will dissolve. At this temperature, the solution is saturated with the solute. The solution contains the maximum amount of solute that can dissolve in water at that temperature. Generally, a given solvent can dissolve more solute at a higher temperature than at a lower temperature. Watch as the solution cools slowly, undisturbed. The solution has more solute than the solvent can normally dissolve at a lower temperature. The solution is said to be supersaturated. As Araceli introduces a small crystal of nickel sulfate, the crystal acts like a seed or nucleus for more crystallization. On and around this crystal, the excess solute in the solution starts to deposit or crystallize. In a few days, we should see a larger crystal. This is the same principle applied in producing artificial rain. Nimbus clouds are seeded with silver iodide crystals. Water crystals form on these seeds, later becoming heavy enough to fall as rain. In a past episode, we discussed how molecules in the liquid phase of a substance have greater kinetic energy than molecules in the solid phase. Molecules of a liquid move past each other and collide with one another. They also attract each other enough to keep them together in a continuous phase. Let's explore this movement in molecules of liquids through a simple experiment. I place a drop of dye in a beaker containing water. Watch how the dye spreads out or diffuses in the water even without stirring. Let's drop the dye into different beakers containing methyl alcohol, ethyl alcohol, and glycerol. The dye diffuses fastest in water and slowest in glycerol. This shows that attractions are stronger between molecules of the dye and water. The tendency of a liquid to diffuse in another liquid depends on the attractions between the molecules. Now that we've seen how molecules in diffusing liquids behave, let's focus on what happens with molecules in evaporating liquids. In a past episode, we looked into solar evaporation of seawater. But evaporation can take place even under the shade. In fact, it can happen at any temperature. If left for some time, the water in this glass will evaporate completely. What happens to molecules during evaporation? Like gas molecules, molecules in liquids do not all move at the same speed. The faster ones, those with higher kinetic energy at the surface of the liquid, can escape from the attraction of nearby molecules in the liquid. They then join the gas molecules in the air. What makes evaporation different from boiling? You can see that bubbles of vapor form throughout the boiling water, not just as a surface as in evaporation. The bubbles of vapor then rise to the surface and escape. The vapor pressure of the liquid inside these bubbles equals the pressure of the atmosphere above the liquid. Boiling takes place only at a definite temperature when this condition is met. Like any other gas, water vapor in the atmosphere exerts pressure. Its molecules collide and exert force on other objects around them. As more water vapor fills the atmosphere, pressure increases until saturation is reached. The atmosphere can no longer take in any more water vapor. We can measure how much water vapor there is in the atmosphere by looking at the relative humidity. The closer the actual amount of water vapor in the air is to the saturation point, the more humid it is. The Philippines is a particularly humid country. Our relative humidity ranges from 60 to over 80% and even higher during summertime. High humidity is what makes us feel uncomfortable. Normally, our bodies release heat when the surrounding temperature is lower than our body temperatures. When the temperature around us is high, we release body heat by sweating. Evaporation of sweat carries away high energy molecules from our body, leaving behind molecules of lower energy. When we fan ourselves, our sweat evaporates faster and body heat is released more rapidly. This is what happens after we leave a swimming pool or bath. The evaporation of the high energy molecules from our skin cools us. During humid days, the air is filled with water molecules. This slows down evaporation of body sweat. Now it's time to cool off with a short break. Different liquids have different vapor pressures. Take these, for example: diethyl ether, ethyl alcohol, water, and ethylene glycol. This graph shows the vapor pressure of these liquids. Diethyl ether and ethyl alcohol have high vapor pressures. This means that they evaporate easily. We say that these liquids are volatile. Water and ethylene glycol have low vapor pressures. They do not evaporate easily. Ethylene glycol is used as an ice substitute. This graph also shows that the vapor pressure of each liquid rises with temperature. We now ask the following questions. Why do different liquids have different vapor pressures? Why does vapor pressure rise with temperature? To answer these questions, let's recall the kinetic molecular theory. We can trace the differences in the rate of evaporation of liquids to how strongly these molecules interact with each other. Molecules of diethyl ether and ethyl alcohol have weaker attractions for one another. Their molecules at the surface then easily escape into the atmosphere. Molecules of water and ethylene glycol have stronger attractions for each other, and so they do not evaporate as easily. Let's look at a very interesting property of liquids. Place a steel blade flat on water. It does not sink even if steel is more dense than water. This seems to contradict our observation made in an early episode that things denser than water will sink in it. There are other intriguing observations we can make about liquid. For instance, why are soap bubbles spherical and not any other shape? And what about water and other liquids rising in a capillary or thin tube? Why do they seem to defy the law of gravity? What makes liquids exhibit all this seemingly strange behavior? A single property of liquids explains all of this: surface tension. To understand surface tension, let's try to visualize what is happening with molecules in a liquid. The molecules in a liquid, except for those at the surface, are completely surrounded by other molecules. Each molecule experiences equal attraction on all sides. On the other hand, the molecules on the surface do not experience these balanced attractions on all sides. These molecules are attracted more strongly by liquid molecules underneath than by gas molecules above, which are further apart and fewer. As a result, the surface molecules are pulled inward and begin to contract. When as many liquid molecules as possible have been pulled inward, the tendency of the surface to contract stops. It has now attained a minimum surface area. Due to this inward pull, the surface molecules act as if in a state of tension. They behave like an invisible film or stretched net that can hold up small objects. To bring more molecules from under the surface or the inner bulk to the surface, some energy is needed. The value of the surface tension is a measure of this energy. And what about bubbles? What makes them round? Among the different shapes, the sphere has the smallest surface area for a given volume. For this reason, bubbles tend to be spherical. This is also why, in outer space, water and other liquids tend to form into perfect spheres. How do we explain why liquids rise in a capillary tube? Surface tension causes a liquid to rise up the capillary tube. The liquid stops rising when the surface tension equals the force of gravity. Knowing about surface tension, we can increase the wettability of liquids. For instance, in washing clothes with detergent. Compared to other liquids, water has a high surface tension. It cannot penetrate cloth fibers well. This is why we cannot wash our clothes thoroughly using water alone. This is where detergents come in. When I place a drop of water on this piece of cloth, notice how long the water keeps its spherical shape. What happens when we add detergent to water? When I place a drop of detergent solution on the cloth, the drop easily spreads out. The detergent lowers the surface tension of water. In this way, the detergent solution can penetrate more deeply into the fabric, making the laundry process effective. Water rises to about 2.5 centimeters in this capillary tube. When detergent is added to water, there is a decrease in this height due to the decrease in surface tension. The tendency of a liquid to diffuse in another liquid depends on the strength of the attractions between their molecules. The vapor pressure of each liquid rises with temperature. Surface tension is a tendency of a liquid surface to contract and assume minimum surface area. In the past half hour, we have looked at the properties of solids and liquids. We saw how the kinetic molecular theory explains surface tension and the diffusion and evaporation of liquids. In our next episode, we will delve into indicators of change. This is your host, Ramon Miranda, saying good day.